What's up everyone, Terry here, and I'm really excited to go through this exact differentials type problem on one that pertains to expansion coefficient and the isothermal compressibility. And well, let's jump right in. So this is the problem here. So we have a sealed flask at 25 degrees Celsius is filled with water. And what would be the change in pressure if the temperature is raised by 15 degrees Celsius? And we're given alpha. Alpha is the the expansion coefficient, and it's 2.07 times 10 to the negative 4 per Kelvin. And we're also given kappa, which is the isothermal compressibility, and it's 4.5 times 10 to the negative 5 per ATM. So how are we going to start this? Well, we want the change in pressure, and we're given this change in temperature here. But let's define what alpha and kappa are, and maybe we can go somewhere with that. So we'll start off with defining those. So alpha is 1 over v times the partial derivative of v with the change in temperature holding pressure constant. And I think of this one as heating a balloon. Heating a balloon in just outside atmospheric pressure. If it heats up, the volume gets larger and atmospheric pressure stays the same, pretty much. And kappa is defined as negative 1 over v times the change in volume over the change in pressure holding temperature constant. So it's similar to this alpha, except we've switched the dependency of these variables here. Now, in both of these cases, we're changing volume, and we're looking at volume as a function of either temperature or pressure. So let's write it like that. We can write volume is a function of temperature and pressure, and volume's a state function. So we can actually write it as a differential, an exact differential. And as an exact differential, it would be dV equals change in volume over the change in temperature holding pressure constant times dt plus the change in volume over the change in pressure holding temperature constant times dP here. So this, I'm not going to get into why this is true, this exact differentials, because we're just working through some practice problems, but you could think of this as the slope with respect to temperature holding pressure constant, and the slope with respect to pressure holding temperature constant. And if this was a 3D graph of V plotted against T and P, we'd see that these change in slopes times the change in each variable would equal to the change in the volume here. But that's really quickly. Sorry if that was too much, but yeah. Anyways, so if we look at this exact differential form, this dV over dt, or del V over del T holding pressure constant, that's the same as this one right here. See that? So we can actually substitute this in. We can solve for our partial V over partial T holding pressure constant. If we solve for that, that's alpha times V. And we can literally just substitute that in. So that's alpha times, what did I say, V dt. And we could do the exact same thing to the other side, where we have part derivative of volume with respect to the pressure holding temperature constant. That's the same as this here. So this term, this partial term here, is the exact same as negative kappa times V. Negative kappa times V if we rearrange it. So I'm just going to plug that in. Negative kappa times V dP. Okay. Now I think we're getting closer because we have this change in temperature, infinitesimal change here, change in pressure here, and we have some values for alpha and kappa here. Now this is a sealed flask, and they don't tell us, but it's implied that if it's a sealed flask, that means the volume's not going to change. Also, this is liquid water. It's 25 degrees Celsius. So if we heat it by 15 degrees Celsius, the volume's not going to change very much, none of the liquid water. There's going to be no change in volume. So we can impose the condition of constant volume. Volume is constant. And if volume's constant, then dV is 0. And we can plug the rest of them in here. Alpha V dt minus kappa V dP. And look at this, we have V on, we can cancel these V's out because we just divide everything by V. And if we move this term here, this kappa dp to the other side to make it positive, we get kappa dp equals alpha dt. And this is under constant volume. So volume equals constant here. And we can rearrange this as a partial derivative. So the change in pressure over the change in temperature, holding volume constant, equals alpha over kappa. And now we can see how the change in pressure is related to the change in temperature with the constant volume here, alpha over kappa. So we can just kind of rearrange this and integrate. dp equals alpha over kappa dt, and this is from our initial to final state. Well, the integral of dp is just going to be our change in pressure. And alpha and kappa, they're constants because they're just given values right here. So we have alpha over kappa, and dt, this is just our change in temperature. And our change in temperature is 15 Kelvin, because that's what we're given right here, 15 Kelvin. So all we need to do is plug in our values, and we're done. So alpha is 2.07 times 10 to the negative 4. So 2.07 times 10 to the negative 4, and that's per Kelvin. And kappa, I think, was 4.50 times 10 to the negative 5 per ATM. And our change in temperature is 15 Kelvin. If it changes by 15 degrees Celsius, it also changes by 15 Kelvin. It's the same scale, just translated a little bit. So a degree is the same as a degree. Okay, so we'll plug that in here. And 2.07 exponent negative 4 divided by 4.5 exponent negative 5 times 15. All right, 69. So 69 ATM. That's our change in pressure. So quite a bit, but remember, this is a sealed flask. So there's nowhere for the gas to go. If it was to evaporate, or there's nowhere for that water to go, it's stuck in the flask. So all of that energy transferred as heat is going to go right into increasing the speed of the molecules, which is going to increase the pressure. So the pressure will increase quite a bit. All right, that's it. Hope you enjoyed it. See you in the next one. Cheers.